everyone, and welcome back to another episode of Science. In this episode, I want to teach you about Newton's laws of motion. Now, forces can be pulls, pushes, or twists, and a force is something that can make an object start moving, speed up, slow down, change direction, change its shape, a whole number of different movements. Sometimes it's hard to tell that forces are acting because they're balanced, and sometimes it's really obvious, for example, in a car accident. And I'll go through both of these examples in today's episode. Now, the great English scientist Isaac Newton, you've probably heard of him before. He was actually the scientist who formulated these three laws of motion in 1687, and these three laws explain why everything around you moves the way it does. So let's get started. We'll start with Newton's first law, and this is the law of inertia. You may have heard of this before, but maybe perhaps you don't quite understand what inertia actually means. Now, to summarize it very briefly, the momentum of an object resisting any change in its motion is called inertia. It's this resistance to change the object's motion that we refer to as inertia. The law explains that an object at rest will remain this way unless it's acted upon an external force. For example, if you've just got a pencil sitting on your desk, for example, it's going to stay sitting on that desk unless an external force applies a force on it to move it. Otherwise, it will remain at rest. Similarly, an object that is moving will continue to move at the same speed and in the same direction unless an unbalanced force acts upon it. This is especially true for when you are in space. If you are in space, there's no air resistance, there's no friction. So if you were to throw a tennis ball in space, that tennis ball would continue moving in that direction you threw it at the speed that you threw it forever until an external force acts upon it. Here on Earth, when you throw a tennis ball, well, there's air resistance providing friction, slowing the ball down, and there's also the force of gravity, which is driving the ball downwards towards the ground. So here on Earth, there are external forces that act upon objects, slowing them down through friction, as an example. But in space, objects will keep doing whatever they're doing unless you apply some kind of external force to them. And this momentum of an object to resist its change in motion is referred to as inertia. Objects want to keep doing what they're doing until an external force acts upon them. A good example I can use is a car accident in this case. So the car, when it crashes into an object, in this case a pole, the car comes to a very sudden stop. However, you inside the car, you are not a part of the car. You're sitting in the car. And so say this car was moving at 60 kilometers per hour. It comes to a sudden stop by hitting the pole, the external force on the car. But you still have that 60 kilometers per hour inertia. That energy is stored in your body. The kinetic energy is in your body. And your body has a mass and it wants to keep continuing at 60 kilometers per hour. And so unless you have a seatbelt strapped to you, holding you down, you continue moving out of the windshield onto the pavement. The external force that stops you is your seatbelt. And so this is why seatbelts are so vitally important for saving people's lives. They act as the external force stopping people from continuing their movement in the case of a car accident due to their inertia. Now, the bigger the object is, the greater the inertia it has. So the bigger it is, the harder it is going to push it, to move it. Or if it's rolling towards you, the harder it will be to stop it. The bigger the object, the greater the inertia, and the harder it is to change whatever it's doing at the time, whether it's just sitting there or whether it is moving. Let's move on to Newton's second law, and this law is F equals ma. This is explaining the relationship between the force of an object, the mass of the object, and the acceleration of the object. Each of these variables are dependent on each other, and we can use a triangle formula to work Newton's second law. F is equal to the net or total force being experienced by the object, and this is measured in the units of newtons, or capital N. Mass is equal to the mass of the object, and always use kilograms for this, always use kilograms. Acceleration of the object is measured in meters per second squared, and when you are doing these calculations, it's important that you always use these units. If it has given you an acceleration of kilometers per hour squared, then you must change it to meters per second squared. Or if it's given you a mass in grams, you must change it to kilograms. It will make your calculations for your Newton's second law much more simple, much more simple. Now this triangle formula is very similar to what we've learned before, similar to the distance, speed, time triangle formula. If you want to work out the force of an object, you go mass times acceleration. If you want to work out the acceleration of an object, you go force divided by mass. And if you want to work out the mass of an object, you go force divided by acceleration. Now I've got an entertaining video here, what if Superman punched you, which links nicely to this relationship of force, mass, and acceleration. Have a click on this video and have a watch of it. In the meantime, let's do a practice question together. I've got a car here with a mass of 1,200 kilograms, and the engine is providing a forward force of 3,000 newtons, and air resistance is providing friction force of 600 newtons. So here I have my mass and I have my force. We should be able to calculate an acceleration from this. The first thing we need to do though is figure out what is the net force acting upon this car. Now the net horizontal force is the 3,000 newtons of thrust that the engine is providing, minus the 600 newtons of resistance. This gives the car a net force of 2,400 newtons to the right. 2,400 newtons to the right in a forwards direction. So what is the net force acting on the car? You go 3,000, take away 600, which gives you 2,400 newtons. Don't forget the N. From here we can calculate what is the car's acceleration. If I come back to this slide here, in order to calculate acceleration, you would go force divided by mass. Force divided by mass. So my force is 2,400 and my mass is 1,200. So if you put into your calculator 2,400 divided by 1,200, which is the mass, that gives you an acceleration of 2 meters per second squared. 2 meters per second squared. And this little 2 is just supposed to be up here. Let's have a look at another question. In this case, the question is asking you to describe the movement of the parachutist. Well, the parachutist has a mass of 80 kilograms, a weight force of 800 newtons, so that's how hard he's being pushed down towards Earth, and air resistance of 800 newtons. So in this case, the forces are balanced. I have equal forces pushing the parachuter down and providing air resistance in the opposite direction. This means that because the forces are balanced, the parachutist is actually moving at constant speed towards the ground. Constant speed towards the ground. Sometimes students can confuse equal forces to the object not moving. But the context of the question is important. Because we have a parachutist jumping out of an aeroplane, They are falling towards the Earth, but because air resistance is equal to weight, they are falling at a consistent speed. If I come back to the car example, in this case, the forward thrust force is greater than the resistance force. So this car is not moving at constant speed. This car is actually accelerating. If this force here, if resistance force was also 3000 newtons, then this car would also be moving at constant speed, and the size of the arrow should match it as well. So when the forces are balanced and the question tells you the car is in motion, that means that the car is moving at constant speed. If these values were, if I just refresh the slide, if these values were 0 newtons of forward thrust, and 600 newtons going this way, that means the car is reversing a direction. But if I change this to 0 as well, that means the car is now stationary. You have 0 forward force and 0 backwards force, so the car is stationary. Keeping in mind that there's still a force acting downwards upon it in the form of gravity. This example here though, they are moving at constant speed towards the ground. Constant speed because the forces are balanced. Let's move on to Newton's third law here. Now you may have heard of this before. Newton's third law states that for every action force, there is an equal and opposite reaction force. And there's a couple of good examples to use it for Newton's third law. The first is a rocket engine thrust. The way that you get rocket ships into space is you burn a fuel to produce a thrust in one direction, and that propels the spacecraft in the opposite direction. Because for every action there is an equal and opposite reaction. So when you have the exhaust coming out from one end of the rocket, that provides a thrust, that provides a push. And so therefore, your spacecraft will be pushed into space in the opposite direction. Another example I can use is a cannon and cannonball. When a cannon shoots a cannonball, it provides a thrust on the cannonball itself, and the cannonball comes flying out. But there's a recoil action on the cannon itself. You'll see if you watch some YouTube videos, the cannon itself recoils back in the opposite direction, and there's often a foot that's dug into the ground to stop it from doing that. Also, the mass of the object plays a part here as well. Because the cannonball has a much smaller mass compared to the cannonball travels much further and at greater speed than the much heavier, much greater mass cannon itself. You'll see this cannon recoil, but you'll see the cannonball go off flying. And this is related to F equals ma. The acceleration of the object is dependent on the mass and the force that's applied to it as well. Because the cannon has a much greater mass, it moves back much less than the cannonball being shot out, and the cannonball is shot out much more quickly as well, at a greater speed. But both of these objects feel the same force. They feel the equal and opposite force. The cannonball goes this way, and the cannon recoils in the opposite direction. However, much less because it has a greater mass. And the cannonball shoots out or moves at a much greater rate because it has far less mass compared to the cannon itself. From here, you want to practice with some private study, so please make sure you've collected the Newton's Laws Goodness booklet from me. You can continue working through your Education Perfect, and if you want to have a read of your textbook or do some practice textbook questions, you can log on to your Jacaranda textbook looking at pages 315 and 321. I hope you enjoyed this episode of Science, and I'll see you next time in class.